a couple of years. My background is electronics, and I've been helping the team in areas, all kinds of electrical things, software, all kinds of different things. But what I wanted to go over is give you a little disclaimer and kind of give you an agenda. The agenda is basically a little introduction, and then why people want to use vision, why people have used vision, FRC reasons. But I wanted to just framework everything. And then some basic concepts in what most vision systems and vision technology out there teams are using. So I'll discuss what are the options. I know there's so many different things you see on Chief Delphi, FRC websites, and all kinds of stuff. So what I'm trying to tell you is we have not actually until this year. So this discovery phase of to do it, but didn't know how to do it. Kind of novice, amateur way up some of his knowledge. And
for us,
I know there's a lot of young teams out there and teams that are challenged by is really complex. It's not something that we don't have time for. So I wanted to basically give us some framework that allows younger want to consider vision as part of their robot. And I'll talk a little bit about the details. I do have a working example, except I can't project it. And we'll talk about the conclusion and then any questions and answers. So that's basically my presentation. So the disclaimer I say is, like I said, we are still novices. We're not vision experts. Our team is just learning. But we finally got vision working this year, and we had a lot of fun. So even for a young team like us, it was very challenging, but we through a little bit of hard work, we experimented and we got it working, and we learned some good things. So that's what I wanted to share.
Good.
And that's what I wanted to share. I'm with ClimbBots, what we've learned. And I wanted to mainly, like I said, get you guys excited that vision is not as challenging as it sounds. Are you guys using vision? Anybody using vision right now? Spectrum is?
We worked on it some, but
Okay.
we haven't working on our robot yet.
Okay.
We've attempted and we played, and then we pretty much
It's like a last priority because people are like, oh, I still can't drive, or
Yeah.
I can't do certain things, and I'm not. So yes, I agree. So as we know about Klein, I wanted to give a little foundation on ClimbBots. We're from Klein, young team, student-led. All the software and hardware mechanical build is done by the students. We're not a mentor-driven like 148 or 118 kind of a. The other mechanical, electrical, software. When they needed vision, when I finally said, guys, we got to do vision, and I went in and kind of did some of the legwork to explore what was out there. So that's pretty much it. I'm, software. I do a lot of different kinds of fields of electronics. So I understand technology, electronics, software, hardware, all that stuff. So that's why I felt it was a good challenge for me to learn vision. I'm not an expert in vision. I'll claim that, but I learned enough to have the robot do some stuff.
good.
So why did we want to have vision? Or why does most people want vision? For us, it was basically we were struggling with autonomous, and especially this year, we set a goal to be able to score, and the only way to do it was with vision. So we've not done it this year. We've not able to score, but the goal we set, so vision was really pushed hard.
And that was scoring during autonomous?
Autonomous.
Okay.
Yes. And the other desire we had was we knew that shooting a goal even manually when you're in teleop mode, it's kind of hard with just manual controls. You need some guidance or assist to tell you you're going to get the goal or not, right? So vision can work to assist you or aid you to tell you, okay, you're going to you have a chance of hitting the goal. So that was our motivation the problem we're trying to solve. And most of the competitions we found, and from past, we know that they're using tapes, and there's always some vision targets defined. So if we get good at this, or at least get some basic, all teams want to have some kind of a vision tracking thing. That was hard to convince our team was that it was only for advanced teams. A lot of teams, especially our team, felt like, we're only 3 years and we don't have the guts and knowledge base to get it done. And we didn't do anything start. So it's doable for people that really want to do it.
Fundraising workshop?
No, that one was canceled. Jess is sick.
Oh,
So wait. Yeah.
okay. Do you know if there's any information that is left here for teams about fundraising?
All I can tell you is that Jess was talking about, probably going to be talking about the grants that are on the First in Texas website.
Okay, okay. Thank you.
Sure.
You know when the vision workshop is?
I don't know.
So when the game got announced this year, 2016,
This is the vision
yes, come on in. One of the things we set, everybody had this wise goal, the vision, but really what did we want to do? And this was our problem we kind of defined from day one. So when the game gets announced, one of the challenges, even for any team, is make sure you set a goal for what are you trying to. Everybody generalizes and say, hey, I need vision, but really what do you want to accomplish? In our case, we wanted to accomplish the goal of, actually there's 3 variables. How to angle the shooter, how to shoot with enough power based on how far you are from the tower. Those are the 2 critical variables for us, and direction. Are we aligned with the goal? That's the 3rd variable. Those are the only 3 variables we set as our target to achieve out of the vision system. So that was our kind of, in software land, requirements. We need to be able to aim at an angle, very adjustable, and set the power. As you know, as you get closer to the goal, you have to go really higher, and you might have to adjust for power. We experimented early on to realize that it's not a 1 power, spin it full speed thing on the shooter. It depends on your shooter, but in our case, the shooter was a double wheel shooter. So we needed a mechanism to trim the power. So that's basically what the variable we're looking for out of our vision system. So the architecture in vision, basically, it's very common. This is pretty much for all vision systems in FRC. But the things that's built in that everybody has access to is these network tables. So any kind of vision system you select has to be able to deliver target X, Y, and distance. As we said, one of the things we were really interested to know is how far we are from the tower. So 3 variables critical to our system is how far up is the goal, up and down, and how far left and right is the goal, and how far it is physically. And believe it or not, we can actually get a distance measurement from vision. It's not as accurate as ultrasonics or any other distance measuring, but it's sufficient to get you enough knowledge to say, okay, you're far close. Okay? Everybody has how to add it to their robot and make it work consistently. So if you look at that architecture, the 3 options that most people see out there are open CV, grip, and eye vision. We've evaluated at least 2 of them, grip and OpenCV. We've had a lot of experimentation and testing. NI Vision, we started doing it, but it was, our main concern is the source code is closed and it only works in NI products. So we were kind of not too excited about that, but we kind of like the OpenCV grip solution, mainly because, and so OpenCV is optimized for real-time image processing. It's available to you, so you can use C++, Python, Java. So if you got programmers in your team that are languages, they can easily start looking at getting examples. There's a lot of open source examples out there for Java and Python. So OpenCV was attractive for us in that reason. And the other cool thing we found was OpenCV actually runs on Windows, any Linux machine, or even the Pi. So the advantage of this, where it is able to run on multiple platforms, for development environment, like when you're experimenting with code, you can code everything in Windows and just take your Python code or whatever and transfer it into where you want to run it. So that's what we've been doing. Yes, there is lots of examples out on the web for doing different kind of things, object detection. We'll discuss that in a bit. But there's obviously the challenge of writing your own. This is more writing your own code. Grip came along and kind of solved this issue of it's a little difficult to code in OpenCV. So right now, and I'm sure you've seen it on First website, and it's designed with First Robotics in mind. Very little programming is required. If it's like a lab view, you just connect the dots. It's very simple, but you have to know some basic about vision. Source code is available, and it uses actually OpenCV. So if you learn things in OpenCV, you can apply it to OpenCV or even stay in the grip land. It runs on PC and it runs on Pi. We, in our team, are actually running it on a PC, on our smart dashboard. So it allows, and I'll talk about how the hardware works for us. Hello. And like I said, NI Vision, I haven't experimented at all. I don't know if you guys have any experience. Any of you guys experimented with NI Vision or?
Just a
little bit, yeah. Any?
We played with grip and we've got some code running on OpenCV, but it's not deployed basically.
Okay.
NI Vision a little bit, but I think for some of the same reasons we decided to stick with the
Yeah. We actually, even at Worlds and the previous competition, we had grip running on our driver station with an IP camera. And I'll show you the. Hello.
Hello.
So in Vision, like I said, this is a very basic introductory kind of a thing. So I wanted to discuss some common terminology in Vision and get everybody on board. The main thing, the Vision thing we're trying to look for is obviously the ability to capture image in raw format, bitmap, hopefully, not compressed. Then the other thing we're trying to do is obviously process the image by either manipulating the image, filtering, masking, changing colors, RGB, black and white, grayscale, whatever is required. And the most important thing for us is actually object detection. Tower detection, example 2016. And the 2 types of detection that we've experimented with is template matching and contour shape finding. And we've had obviously a little bit easier success with contour shape finding because it's available in grip. So yeah, those are the basic concepts of vision. You have to be able to take an image, process it, do something, and then do this. Now, one of the things I want to give you a little lessons we learned from here is you can do a lot of mathematical manipulations in Robo or Raspberry, but if you can do things physically, like filtering directly right before the image even gets scanned into the camera, that'll save you a lot of processing time. And simple things like optical filters, and I'll give you a picture, polarizer glasses will save you, increase your tricks is to kind of, if you think there's things you're doing in your with hardware, optical filters, or even it's a good way to save CPU time and get high frame rates. High frame rates is not a very critical thing. Actually, we found out we're running about 8 frames per second and still being able to control our robot. So for 2016, obviously we try to take advantage of the tape, and we're obviously using the green rings. But what I was trying to say is this optical filter is actually saving us some processing time. And this was actually one of the tricks that even if you look at these test images that we're getting from FRC, if you notice how dark they are versus how they're lit up they are, they're using some filtering too, directly on the cameras. And the reason these filters help is the contrast ratio, but when we shine these lights to the background, like the ambient light, is very high. So actually what happens is if you shine too much light on it blurs out, and it's hard to get contours on those. So physically using, an example what we do is just found some old sunglasses, polarizers, ripped the lenses and put them on the camera. Easily got our image processing a lot faster. So it's not difficult, it's not expensive to do that. But definitely get polarizers for your webcams, and that'll help a lot. And basics of how our object detection also works is we're taking the image in, and we actually blur it a little bit because we want to get rid of all the speckle noise. Once we've actually blurred it, we get rid of, desaturate it, get rid of all the background information, do some filtering, and then we actually detect the edge. Now, one of the things what we look for in our object detection is when we do a contour map, we're looking at number of vertices. If you look at all these shapes, a vertex is basically corners, right? On this, how many corners do you see? 8. And we don't hard code a 8 in our object detection. We kind of say between 6 and 10. So when we're doing a contour detection where once we figured out where the shape is, the first check we do is make sure we got between 6 and 8 corners. And that tells us, okay, I think that's close to what we're looking for, which is the goal. Oops, sorry. And then the next thing we do is we actually look at the aspect ratio, make sure it's square or close to a square. And so I don't want to confuse you with some of the terminology, but in short, using the aspect ratios and vertices and contour is what is helping our vision detection. So originally we started to do this where we're actually using a Raspberry Pi and putting OpenCV on there with Python and a camera, which was then feeding the data to the network tables. The hard part was debugging this code. We had a hard time debugging this code. Mainly because You're running in a virtual kind of a remote admin connection. It was very hard to adjust values, parameters, change code. It's doable. I think it's very doable, but if you want to experiment, I think what we found was this was the easiest path to make it work. The drive station runs the grip software, and you can use the IP camera, or in our case, we use a Raspberry Pi just to do the IP camera. We can actually hook up multiple cameras on a Raspberry Pi and MPEG stream them, JPEG stream them actually. And that's what we're using in grip to manipulate and object detect. As you know, there's only one Ethernet port on the new radio. So that's one of the reasons we ended up using the Pi. We can actually hook up multiple cameras and stream them using the Pi. And if grip, we can use grip to actually do some calculations and come up with this. So this gives us the flexibility to add more cameras. Now, the caveat there is obviously there are rules in the FRC game rules as far as how much the bandwidth you can use for the IP cameras. So make sure you don't violate the rules for bandwidth on the cameras. I think it's like 4 megabits or something like that. I don't know the exact number, but it's just be careful. Don't try and make an HD image and try to transfer it over and try to, but I don't have a demo today. Unfortunately, our system's down. So my laptop, I left the adapter and stuff like that. So I'm kind of out of a demo. But that's pretty much my presentation, and I don't have anything to demo right now. If you have any questions, that's all I can say. You guys missed everything. But she's your expert now.
Yes, yes, I am overqualified now.
Any questions? Yeah.
So when we were doing vision with our robot, what we would do is we would set up and we would have the camera inputting the visual feed to the kangaroo, and the kangaroo was running grip on it, and grip was feeding information to the network table for Java, right? And we got that all up and running, but when we actually had vision onto the what's it called? When we actually had vision running, I couldn't figure out a way to try and like, how did you guys make the robot analyze like what it was seeing? Like it had the vision, it had the goal set up, but how did you use that to manipulate what your robot was going to do?
Okay, so one of the things we did, with our target, let me show you this picture here. This shooter, our shooter which can go up and down and go sideways, we made sure that our camera moves with our shooter.
Okay.
So our design goal was, if the camera is able to see it in other words, if obviously nobody shoots, but anyway, if you're shooting, what do you do when you're shooting? You have a target, a square, right? So same thing with our camera. We're setting a target in the middle, and saying, okay, if our contour is here and our target's in the middle, we got to shift over and go up.
Okay. Does your camera automatically do this? Or
Yes.
Okay.
So we have two buttons, one for going up and down. So once we see that the shape is here but our thing is off target, that'll immediately push it up, and then the second button will align the robot to the thing. Now we can automate that with one button. We just didn't have time to manipulate all that to work. Like anything else, we ran out of time. But I think you can basically do it together simultaneously, where it would, what they call coordinated move, where you can go up and move at the same time and do a 45. But this is the kind of stuff you can actually experiment right now during summertime. So if you guys can practice with your robot, anything that drives with something that goes up and down, just keep refining that code. But ideally you want to be able to do it together, right? Because it's all time, right? We're trying to get a second out of every little motion, right? So
yeah, so like when we were doing the vision on our robot, what we would have it do is we would have it start off to the side where it didn't see a goal, and then we'd have it turn into the vision of the goal.
Yes.
And we kind of had trouble aligning the goal with where we wanted our robot to be. So like, did you guys have any problems with that? Like, because we were, say the goal would be here, our robot would be facing this way, it would turn into it, and then it would see it, but it wouldn't react fast enough into which it could stop and actually pinpoint the location which we wanted to shoot it at. It'd kind of just oscillate between where we wanted it to go, and I wasn't quite sure how to fix it.
Do you guys use PID or regular on-off kind of a?
We were going to use a PID, but
Okay.
I really, we didn't use a PID for vision, we just did a normal.
So yeah, I would recommend using PID. That's what's going to get you the, otherwise it's just going to bounce back and forth.
Yeah, that's what we're doing.
So that's one thing that's easy to do in the beginning, just to home in and just stop, but then you're not at the right spot, so you're going back and forth. We had the same problem. We still have the same problem. So you got to iterate. There's two ways. One is either use PID or iterate and asymptotically get to your target, but that costs you time.
Yeah.
The best way is to actually, if you can calculate how far it is and how much you want to move to get to that angle. So one of the things we actually did, remember I did an Excel spreadsheet, collected a data sheet, and basically made a polynomial equation for angle versus how far it is. And the way we found out how far it is the shape I just talked about right here. Where was it? Okay, this size of this shape, the area of the shape, if you take the area and then you take measurements for X number of points,
You can tell how hard to shoot.
how far it is and then how hard to shoot, yes.
Okay.
So that was the method we used to determine the power. But that area is actually very useful. It actually was, we turned it into a distance measure, and we took the distance and turned it into power.
Awesome.
Now you can have another equation which biases the power a little bit, a second factor for angle. How that X tends, where if the goal is skewed a little bit, you can change your power again. So, but the key thing is to take exact measurements and come up with the formulas. It is very important to take those data points. It's not a straight mathematics calculated out. You must take the data from your robot, because the power, all that comes from your robot. And the other compensation you can do is the Talons now have the power current measurement. You can even do a PID on the current to actually get the power. So we haven't done that, but that's one of the things we're thinking of, actually getting a consistent power level. Right now we just set the RPM voltage, but we need to actually set the current, not just the voltage.
Okay, thank you.
Okay? So, I mean, that's pretty much all the simple lessons we've learned, but I would recommend grip works for quick experimentation. Summertime, use that time to, because on a PC you can even work at home and whatever you can do, and a webcam, and experiment and get familiar with it. Some of those concepts you can reuse in OpenCV as well.
What is OpenCV?
Okay, so OpenCV, it's a computer vision processing library that actually runs. It runs actually on the Windows, Android, and Raspberry Pi. It's basically for what's behind grip is a little bit of OpenCV.
Okay. So it's just image processing?
It's image processing, that's all it is, yes.
Awesome.
But you can write code in Python, Java, or C++. There's a lot of Python code for OpenCV out there. So our code tracker and all that that's on Chief Delphi is in Python, OpenCV. And I know other teams are all using most OpenCV or Python. And the cool thing for me, I was interested to run it on the Pi, and that's why we originally started with using the Pi. Any other questions?
Did you actually run the Raspberry Pi on the robot?
Yes, we did.
Do you ever have any problems with, like when your current get down, like your tire reading or something like that?
Okay, so the Pi 2B is very sensitive. The older ones are not. And Pi 3, I think, we found with Pi 2, actually, power sensitive. But the new Pi 3 is recommended. A lot faster. It's more processing.
But for your actual competition,
We're actually using a Raspberry Pi right now for just turning it into an IP camera. And it's been very successful. But our intention is to move on and use Pi 3s, obviously, too. I still think this is the way to do it, because that would be degrading our performance, I think. So make the code run a lot faster. So especially for quick aiming and so all the optimization, I think, is going to require hardware, not going through the drive station. This is like slow. But it is very. The other benefit we found using the drive station, actually the drivers were able to use the contours to manually aim. So even though it didn't do the full thing, they were using it just to manually aim. So it's a backup way of getting the drivers to aim properly.
And was there a marked increase in your robot performance last year and this year? I mean, knowing what you know now, you're going to continue forward all this?
Definitely. I think from now on, our team, they're not going to be afraid of vision. I think they're just going to take what they have right now and just try and make it better. Like I said, a little faster. Experiment with a little bit more advanced projects, how to drive better. One of the things we have to do, obviously, with this is integrate gyros to be able to get proper direction. So autonomous, you definitely need gyros. So I think now they feel more comfortable using the other advanced stuff like gyros and all that. Once they know they're getting reasonable vision information. So yeah, we will definitely continue using it. Is it perfect? No. It's never perfect.
Like somebody...
The happiest moment was the day when they pushed the button and the thing just went up there, and then they pushed the fire and the thing shot a goal.
So that was all worthwhile.
That was the magic. That was the magic moment for the team.
That's a good day.
So, but that's all using. We ended up that was all using this drive station grip business. So I can't imagine if we even start doing this, how much better it'll get. Because the camera information needs to be a lot faster. If we can get 15 frames per second, I think that would be a lot more performance to aim for.
Oh, we can use an Android device to do the same thing, right?
Yeah.
For the first part, yeah. So the image processing is done in the phone, and then it's being transferred to RoboRio?
Yes. Anything that can publish to network tables can work. I think the way the RoboRio is designed, it's all this thing, the whole architecture is dependent on these network tables. So not only vision, it could be other systems too. Say you put some magic sensor, not vision, but some who knows what. If you can put stuff in the network tables, the RoboRio can use that data.
And
So-
it doesn't violate the rule of FRC?
No.
Like if I use a phone, then the battery won't be a factor, right?
Power has to come from a
For the
the,
full suit.
yeah. I mean, you know, we can use flashlights even without
Yeah.
direct hooking up to the battery on the robot. So, and there was no secondary power devices. Any other issues, questions? Summertime is a good time to experiment, even fall before the competition gets started. My suggestion, start early experimenting and get a couple people, you know, to try different things. But grip is an easy way to start testing and get going and get familiar with the vision. And it's just a...
So I get to go buy a Raspberry Pi 3, that's my job.
Pi 3, yes, yes.
Yeah, my job is to buy. Their job is to figure it out.
Not one, buy a couple.
Buy. Oh, shoot. You're a bad mentor.
One is just a backup, you know.
Oh, yeah, now tell me it's a backup. Okay, and so if Pi 3 is out, get that one.
Yeah.
Okay.
In fact, I'll go one step further. Sometime during the fall time, I'll publish all my code that's running on the Pi as well.
Well,
So our team will make it available on a... Okay?
okay. Well, we're spending a lot of money.
You're gonna run out of money, Susan.
No, you're getting a lot of education. That's what, it's an investment.
Pi is pretty inexpensive.
Yeah.
$40 for
Yeah, I know.